Good afternoon, ladies and gentlemen of our two honors. Graphing cubic functions is where we're starting today, and so we're going to spend some time at the beginning of class just kind of going over some things, and I hope it's going to be somewhat familiar to you as we go along. So the essential question, how are the graphs of f of x equals a times quantity x minus h squared plus k related to the graph of f of x equals x cubed? And what I'm going to do here is just sort of write out the function. So we have f of x equals a times quantity x minus h cubed plus k. So let's review briefly what these different parameters do to a cubic function. Basically, we call this one here x cubed, we call this a parent function. And basically, all transformations of this parent function are going to be like children of this basic parent function, essentially. So that's the logical representation of it. And so in this function right here, what does a do to the function? Pardon me? Okay, Ben said slope, kind of, but I'm going to go ahead and reword it. Basically, it'll affect, effects, if I could spell effects, would be really good. Affects width and narrowness of graph. Okay, does A deal with anything else besides the width and the narrowness of the graph?
Yes.
Yes, it does. What else? What else does A do?
Besides if it's pointing up or down.
Okay, so Jason decides if pointing up or down, so kind of that way. So let's put it this way. If A is less than 0, then f of x reflects across the x-axis. Is that what you meant, Jay? Okay, so that would be the properties of A. Next, we have this h. What does h do? What does h do to the graph of the function? Pardon me? Vertex? Here's the odd thing. Ben said vertex, but oddly enough, in this context, we do not deal with vertices. It's not a vertex. It's something that's the vertex would be like an endpoint, like if you had the quadratic function. Okay, your vertex would be right here.
Isn't it right?
Yes, okay, so let's go ahead and do this. So Gabby says, what would be the word for it? What right and left? Translates. And really, translates f of x left and right. I'll just put left/right. Now Gabby happened to have used the kind of the conventionally accepted algebra word, which is translates, but are there other words that could you could use besides that? What would be some other words?
Slide, yeah.
Slides,
Shift.
shift, move. Now, somebody in the 7th period said maneuver.
Yeah.
Okay, and so that's, so anyway, just different things. And then what does K do? Yeah, so really it's going to be translates. The graph. Up and down. So we're going to explore these things a little bit. All right, thank you. Okay, and then we're going to analyze key attributes like domain, range, intercept, symmetries, asymptotic behavior, maximum and minimum, given as an interval. And I'm glad Ben mentioned vertex, because there's something I didn't mention in the other classes I think is important that's very much related to a vertex. We'll talk about that in a little bit. Here we're given Explore 1, graphing and analyzing f of x equals x cubed. And so basically it says here, it's pretty hard to read, a cubic function has a standard form of f of x equals ax cubed plus bx squared plus cx plus d. And so we have a, b, and c, and d will all be real numbers. And the basic cubic function here is f of x equals x cubed, basic parent function. And for the family of functions, and here we're given a table to fill in some values. And so if we go plug 0 into y equals x cubed, what do we get as an output? We get 0, which is right here. And then if we plug in 1, what do we get? 1. If we plug in 2, what do we get? You get 8. So here we have our points like this. And if we plug in -1, what do we get? -1. If we plug in -2, we get -8. And so our points are going to look like this. And if we tie them together, we're going to get something that looks like this. It comes pretty steep, and then right as it approaches the x-axis, the thing kind of turns sideways and then resumes upward from there. Okay? Now, Ben mentioned vertex earlier, but when you have it like this, where we sort of change direction from this going this downward curve, upward curve, we call this an inflection point. Or sometimes you'll hear that said as a point of inflection. And the thing about it is that we deal with points of inflection a lot more for those of you who are going to go into calculus, how to find inflection points. But that's a good addition. So it's not exactly the vertex, is it? But it's kind of good. It's a symmetrical center of this curve, isn't it? Even though it's not technically a vertex. Okay, and so now we have, what is our domain of this function? Well, we're given this script R, which means all real numbers, or if you write this in interval form, looks like this, right? And then what is our range going to be? Our range is going to be the same as our domain, isn't it? All real numbers. And then our end behavior, as x approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, f of x approaches negative infinity. And the zeros of the function, well, we have x equals 0. where does the function have positive values? Well, they give you the answer for when x is greater than 0. Next, where does the function have negative values? Well, where x is less than 0. And then, where is the function increasing? As we go left to right, where is this function increasing? The whole thing, everywhere, right? So the whole thing, so you can say everywhere, that's kind of a verbal answer, but you could say on the interval of greater than negative infinity to less than infinity. That's where. And then verbally it says where the function is decreasing, the function never decreases. And then the very last row there says that the function is the function odd or even. And then it gives little explanations of what they are. F of negative x equals f of x, that's even. Or f of negative x equals negative f of x.
Odd?
Well, yeah, it's going to be odd because what?
Rotational symmetry.
Yeah, this has rotational symmetry about, and actually it's because of this, because f of negative x equals negative f of x. Do you see that? F of negative x equals negative f of x. Because, well, but I like graphically because f of x has rotational symmetry and also when we say rotational, it has 180-degree rotational symmetry about the origin. And I'm going to show you that. Okay, right now, I'm going to go back to this graph here. And if we rotate this thing 180 degrees, what do we get? Itself, right? Reflects upon itself. So that would be graphical evidence of that the function is odd. Also, there are other functions, like if we take this one and move it, and we translate it down 4 units like this, does this thing have rotational, 180 degrees rotational symmetry about anymore? No, it doesn't, right? It does not, but it still has what I call the odd nature. So the way I like to put this is this, that polynomial functions are odd, even. Okay, that's something the cheerleaders need to be giving us, right? Odd positive, odd negative. Odd negative starts high and ends low. Even positive. Even negative. And disaffected. Okay? Questions on that so far? Okay, we're gonna do a few exercises on this. Okay, so we're gonna do this Explore 2, a few things here. Predicting transformations of the graph of f of x equals x cubed. Okay, it says now predict the effect of parameter h on the graph of g of x equals x minus h cubed for each function. So this comes back to what Gabby was talking about earlier, doesn't it? Yeah, it does. The graph of g of x equals x minus 2 cubed is a what? Okay, somebody besides Gabby, what is this going to be? Is a what? Is a is a translation of the graph of f of x right, up, left, or down 2 units. Right. You knew that, right? And the graph of g of x equals x plus 2 cubed is also a translation of the graph right, up, left, down. That's going to be left, right? Now when you took the test, by the way, it reminds me of the test. When you took that test, were you able to answer questions related to this without using a calculator? Yeah, should have. Let me give. I didn't give you your reward yet, did I?
No.
Here. Yeah, so. We had some other good scores on the test too. Promise you that. Okay, but just reminded me of that. Okay, B, predict the effect of parameter k. The graph of g of x equals x cubed plus 2 is a what? Be a translation in which direction? 2 units up. And then the graph of g of x equals x cubed minus 2 is a translation down 2 units. Okay, and you pretty much knew that, right? Okay, next we have C, predict the effect of parameter A on the graph of g of x equals ax cubed for each function. The graph of g of x equals 2x cubed is a what of the graph of f of x by a factor of what? This 2x cubed is a what? Okay, he says dilation. Well, dilation is usually what it is for dilation. If we're going to dilate this circle here, we would dilate it in all directions, kind of like this. So the word isn't exactly dilate, but it's a related word to that. And we've used it. Well, I will tell you what it is a vertical stretch. Anybody remember that? And by a factor of 2. There we go. I accidentally hit my little activator on the pen. Okay, the graph of g of x equals negative 1/2 x cubed is a what?
Vertical compression.
Vertical compression, huh? Of the graph of f of x by a factor of 1/2 as well as a what? Reflection. Reflection. Across the x-axis, yes. Okay, so that's that. And what I have next, and I'm not gonna go on this B at all here. What I have next is I'm going to hand out a sheet for you to get started on. That is just going to do this problem right here, which is related to the first thing we did with that table. I had you do that table and so forth. So you can get started on this here for the rest of class time today. semaphore, isn't it?
Yeah.
Sign for letters.
Yeah, no, like.
Oh, yeah, that's right, the functions. Yeah, you can do hand signals, or, yeah, y was x squared, and x cubed is like that, yeah.
In the back of the head.
Yeah, no, that's true. Where did you see that? That's pretty
It
good.
was, it was a meme.
It's a meme, okay, very cool. Well, it's not exactly that, but it's related to it, right?
Yeah.
Yeah.
G, basically, what they're trying to do.
Yeah, I'll tell you what, we're gonna work on this one here. I can do a Johnny Cash song today,
Let's do it.
because I did one.
That's perfect.
Yeah, Johnny Cash, we got Jay, Justin's Johnny Cash t-shirt. So I want you to do this. This is very similar to the notes we were taking, so just work on that, and then we can just leave that for the rest of class.
Yes,